Okay, this is Unit 17, Part A of the course on mathematical signal processing, mathematical methods for signal processing. And we are at a very critical point in the course in the sense that we have now all the ingredients that we need to do a lot of things that you cannot do otherwise, or that you can do only with a lot of technical effort. So it's like spending energy to climb a mountain, but now we are at a high plateau and we can walk around. So of course it's a huge plateau and we have to understand how things are going there. And I would like also to compare classical approach to Fourier analysis in the spirit of abstract harmonic analysis to what I'm doing now as a kind of globalization procedure. Whereas standard approaches start with Fourier series, then go on to the Fourier transform, then do multidimensional signal processing, and then try to explain how to connect these different things, but only discuss this very little. We have a big universe of what I call the space of mild distributions. And in this world, you can do all these things: discrete, continuous, periodic, non-periodic, and so on. And of course, we have to see how this classical stuff is embedded into this environment, but also how to connect one with the other by taking the appropriate limits. And these limits are always the weak star limits. It's a crazy word or a bad word, but it's the natural kind of convergence. So the two pictures I would like to use as a starting point for this course are the one that you see already on your screen, which is a picture for the Banach-Gelfand triple. You will see this quite often in the future. And what you know so far is the interior circle, the space S0, the Siegel algebra, a nice subspace of functions which is rich enough to contain all the piecewise linear integrable functions and many other functions. It's a good domain for the Poisson formula, but it's of course much smaller than L1. Now, L1 is not invariant on the Fourier transform. You have seen all these pictures of function spaces. Therefore, L2 is much better. So we have seen L2 a little bit in the context of Plancher's theorem as an extension of L1, or actually of L1 intersected L2. We're taking limits. Now, everything, all the spaces that we are interested in, including all the LP spaces, are inside of S0 prime, the dual space. I'm using sometimes a star, sometimes a prime. So it's just saying all the linear functionals. And it's a good way to think of S0 as a space of test functions, and S0 prime as the space of all these possible signals which you could measure. And of course, you measure them with linear measurements. You expect that if you measure 2 times the signal, that you get twice the same complex number if it's a measurement in the complex domain. So it's very much like the story I told you about the polynomials, where we had the cubic polynomials as the signal space and the functionals on the space of cubic polynomials as a completely different object. But now we are in a nice situation because the small space is embedded into the big space. And it was the topic of last course to show you that S0, and therefore also L2, L1, and everything which contains S1 is weak star dense in S0. Now, later on, we will see, hopefully, that you can get an approximation in this weak star sense by just saying, okay, S0 prime contains something like a Dirac comb, which is neither decaying nor a smooth function. So you have to improve on both properties. How can you do it? Well, first you multiply with a kind of plateau type function, a trapezoidal function. So you get a finite Dirac comb with a lot of Diracs near the origin. Let's say all the Diracs from -500 to +500 are surviving, and a few of them are damped. And then from -2000 and outside of -2000, +2000, there is nothing left. And then that localized version is smooth. So you convolve it with a very narrow Dirac-like Gauss function. That would give you a function in S0. Now we don't have all these necessary tools, so we had to do it in a little bit more complicated way. We had to say, take a function, now a signal, a distribution in S0 prime, take a mild distribution, convolve it with a test function, you get a bounded continuous function. Only then you localize it, you get a compactly supported function, which is definitely in L1, and then you convolve it with a Gauss function or anything in the triangular function, which is very compressed and Dirac-like, and because S0 is an ideal in L1, we kind of pull everything into S0. Okay, so we have this situation that you can, in the weak star sense, approximate one thing by the other. Now, the other picture which I produced now for this course is this one, where I have to give up my idea of how things are related. I just wanted to show you, we have this universe of all the mild distribution, and of course it contains the bounded measures. In particular, it contains the discrete finite measures. And we have seen that these are the linear combination of Dirac measures. So you put some Diracs at finitely many points, and then you get a discrete measure, finite discrete measure. Now, we have also seen that the Fourier transform of discrete measure is a pure frequency. So you get the trigonometric polynomials, and I was trying to do it in this way that if you take a Fourier transform, you rotate by 90 degrees, but that's only here. So trigonometric polynomials are also in this space. But on the other hand, if you give me a trigonometric polynomial, I can go back and you get the discrete measure. But you can also take the algebra of absolutely convergent Fourier series. That would be trigonometric polynomials summed up in a way that gives you a continuous function which has an absolutely convergent Fourier series. And then it would have a Fourier transform or inverse Fourier transform, and that would be a discrete measure sitting on the lattice. Now, we also have seen that the small space S0 is inside. And we have also seen that there is consistency. We have an abstract Fourier transform, or extended Fourier transform on S0 prime by this standard rule, sigma hat of f is sigma of f hat. But we also have the integral transform, and of course, this original definition with an integral is extended by this extended Fourier transform, as the name says. It's justified, you have special case. Now, one thing that I was announcing already is that we are going to discuss the situation of periodic and discrete measures. So these are unbounded, clearly unbounded measures in the sense of action on C0. They're not bounded, but they are sums of Diracs, and they are still belonging to S0 prime. We will see this in a moment. They will have a Fourier transform, and that Fourier transform, so the extended Fourier transform applied to a discrete periodic signal supported on a lattice, even multidimensional, will be shown to be realized by the FFT. Okay, now the point that I was making until now is that S0 is weak star dense. So if you know the Fourier transform in the classical way with the Fourier transform, you go to this way. We know that it's the same for discrete situations. You can take discrete measures sitting on very fine lattices, and then you can approximate the continuous integral. This is done in a hand-waving way in many books and presentation, but we will see it's actually a weak star limit. And because you can do this, you can also do it with trigonometric polynomials and even with the periodic discrete Fourier transform. So you can say, if you accept the collection of all the FFTs of appropriate lengths, but then you embed it into S0, and this embedding is almost never discussed. We will discuss it in this course in more detail. Then you only have this possible choice of extending the short-term, the Fourier transform from the FFT setting to the general setting. So if we have a good procedure to approximate a general element by periodic discrete measures, we use the FFT algorithm to compute their discrete Fourier transform, interpreted as extended Fourier transform of some other object, and then go back to the Fourier domain. We will also get another approach to the extended Fourier transform. Maybe this last part is a little bit more difficult to understand. Now, let me quickly try to see. I'm not sure. Yeah, one collection of properties of S0. So we have collected many properties, but one extra property that I wanted to add is the invariance property under the dilation operator. Now, in the original script, you find a table of dilation, stretching operator, all the other operators, and how it's compatible with the classical Fourier transform. So let us just recall that we have, for good reasons, two forms of dilation operators. So D can write for as dilation or Dehnung, drücken, and ST for stretching or stauchen, strecken in German. Now, the D row operator is the value preserving. So it only changes the position of the function, and therefore it doesn't change the values. So it's like running through the same graph, the same curve, but at different speeds, okay? And it's also, of course, compatible with pointwise multiplication. So it's the right dilation operator on the bounded continuous function, and of course also on C0. If we define by jointness, so that's well defined for any bounded measures, the joint operator, and the joint operator always means you get the joint operator on a functional by applying that measure that you want to stretch to the dilated input function. Now, if you do this by saying, well, I know that integrable functions are defining bounded measures, you can do it directly on the function values. Then you get the stretched or compressed version of X is just the renormalized version, which preserves, while the bounded norm is the L1 norm in this case, the area preserving compression. So this is, of course, what we are using when we want to generate Dirac measures, because we want to have that we get a Dirac with total mass 1, and the limit if the functions of non-negative functions have area 1, for example. Okay, so the claim is that our space S0 is good with respect to these operators. Any either stretching or dilation operator leaves the space invariant. Now, this means that we can apply these operators, and of course, we have to prove it. And the interesting part is, if we do only a compression in the sense of value preserving, so we take the graph and make it more and more narrow. That's the case when you want to compress a triangular function to a narrow triangle without increasing the peak value. That's the operator that will be uniformly bounded. So all the triangular function with the basis less than 1 are all uniformly bounded in the S0 space. I mean, actually in the Fourier algebra, because they have common support. The same thing in the opposite direction is, of course, then valid for the ST row operator. So here you're taking not compression, but you're stretching. So you take a kind of mean value. You make, if you would start with a box function, you would have a box function from -100 to +100. If you stretch by rho equals 200 from -1/2 to +1/2. And the amplitude would be 1/200 because the area should be preserved. So that operator is also uniformly bounded. This family of operators is uniformly bounded on S0. Now, the arguments are actually not very deep if you choose the right characterization of S0. The first one is, we have by definition more or less that the ST row operator leaves the L1 norm invariant. We also know that the ST row operator goes over to the D row operator if you go to the Fourier transform side. And we take the norm of the L1 into the Fourier domain, so that's clear. That means we have a D row operator which is not only uniformly bounded and isometric on C0, but it's also isometric on FL1. We also recall that if you take rho large, then it means that the support will shrink. So whereas small rho has a stretching effect, we are now talking about the situation rho larger or equal than 1. So if we start with the atomic representation of an element of S0, it's a sum of little things concentrated on balls of radius capital R with some centers. And because of this dilation effect, of course, we will get them in smaller balls around other centers. I mean, the center is also moving, but these are free, they are floating, that's no problem. And that, of course, means that for any atomic representation of the function f as a sum of atoms, we get another atomic representation, which is even kind of better, potentially better, and we can estimate this. So in this case, we even have this situation. Okay, I see. Now, if you would have a general rho, even one which is doing a stretching, then you would have to decompose everything into, or you would have atoms which are not living in the same ball. And therefore, you would have a constant which depends on the size of the ball. Remember, we had an equivalence constant for every radius. So also for the new radius, r divided by rho. And if rho is a kind of a stretching operator, that would be a constant which has to do with the number of balls that you need of a small size to cover a big ball or so. But as I was already indicating, and that was my focus before, if you're doing compression in the sense of shrinking supports, then you can even have 0 equal 1, and that's the statement that we have here. Now, the second statement is quite clear. If you recall that S0 and D rho are really invariant with are changing their roles under the Fourier transform, because the Fourier and the inverse Fourier transform behave very similar, and of course these operators commute with the flip operator, so there's no problem to transfer the result in the first statement to the second one by just applying the Fourier transform. Now, we also have mentioned that the dual operators are the joint operators are exactly switching the role of D rho and S0. So it means if we have these, maybe we go to the second point, these compression operators, so the area preserving operators, then they act uniformly bounded on S0 prime. I hope I have. No, I'm not sure. I think I have to correct it. It should be rho larger or equal than 1. It's not. I shouldn't change it. It's just the D rho, but I will check it. Now, the statement that I also wanted to show you is, yeah, it's page 142. Something that I think I have already discussed, but I would like to recall to you. It's the statement that the extended Fourier transform, so the one which maps a 0 prime into a 0 prime, is weak star continuous, which simply means if you give me a weak star convergence sequence, a bounded, I would say a bounded sequence of such functionals, and whenever you apply it, it is convergent to sigma 0 of f, then the same is true for the Fourier transforms. Okay, and the proof is just a one-line proof. What is f of sigma n applied to f? It's just sigma n to the Fourier transform of f. What is this? Well, this is just one of the possible elements of S0 due to the Fourier invariance of S0, so you see how important that is. By definition, for every element, you fix that element. This goes for n to infinity to S0 of the element. but then you write it back to extended Fourier transform at the 0 of f. So this is quite easy and quite clear. And so I wanted to show you some examples of this kind of convergence. Yeah, it's maybe a strange example, but giving you an indication of how we can work in this free world of mild distributions. It's actually an example that I learned from theoretical physicists many years ago, and I couldn't understand it at that time. In signal processing, we are talking a lot about the chirp signal. It's a frequency sweep. So if you think of an acoustic realization of this, you see the frequency is increasing with time. Derivative of what you have in the exponent, so it's clearly 2 pi t is a linear thing, and that means you have a linear frequency sweep. So the acoustical picture would be something like increasing linearly in time. Of course, I could have started the STX program and I could have shown you the spectrogram of this. You should have seen a part of a straight line. So the chirp normalized like this would correspond to something which is increasing at 45 degrees. Now, I always say that the Fourier transform is rotating the spectrogram by 90 degrees, and that's compatible with the claim that the extended Fourier transform of this object is well defined and that is giving the chirp again. So somehow, if you think of e to the minus pi t squared being the Gauss function, which is invariant, you can say it's a purely imaginary Gauss function, and therefore it's plausible. We will hopefully discuss it later, but I'm not sure. So just I tell you, this is a bounded continuous function. Obviously, it always takes absolute value 1, and it's continuous, even differentiable, and so on. But this therefore has a Fourier transform in the sense of extended distributions. CB is a subspace of a 0 prime, because you can easily integrate against all the L1 functions, not only S0. Okay, but that this is a Fourier transform is well defined is an interesting thing in the sense that you can say the Fourier transform exists and it is again a bounded continuous function defining a functional. Now, if you take the chirp signal and you do a compression, then the claim is that you get the Dirac delta. So when I saw this the first time, I thought, no, this is nonsense. I mean, you have to have unit mass in order to be able to claim that you can concentrate that mass more and more, and then when you shrink it. Now, the chirp doesn't have mass because it's not integrable. It doesn't have finite support or good decay at infinity. So how can it go to the delta 0? And still I'm saying that, and I'm using now this symbol, a 0 prime weak star limit for rho goes to 0 of S0. So you say, I'm compressing the chirp. I make it for rho equal 1/100. I make 100 times a compressed chirp, and I claim that this goes to the delta 0. And now, how can I prove it? And the proof is very simple in a way, using the two facts that we have. The Fourier transform of S0 of the chirp is, of course, d-rho of the Fourier transform of the chirp. If you take d-rho of the chirp, it goes to 1. Well, this is something that you, of course, have to do in more detail, but think of the e to the I pi t. We are claiming that these guys are uniformly bounded, therefore you're only testing them against test functions which are compactly supported. But over a compact set, if you stretch this at 0, of course you have e to the 0, which is 1. So the 1 is expanding and you're approximately 1 on a very big set. So when you apply this to some f, it goes to, of course, in the weak star sense, only to the 1. So the compression of the chirp in the ST sense is corresponding to the dilation of the chirp on the Fourier transform side, and that goes to 1 in the same sense. Yeah, here you have maybe the detailed argument. because of the boundedness of the chirps or the dilates of the chirps as a bounded family, because I mean all of these chirps, even if you dilate them, are bounded in the space of continuous bounded functions. Therefore, they're all bounded in the domain of 0 prime. So if you have something which is convergent on a dense subspace, and therefore I can restrict my attention to something which is compactly supported, you're kind of living on the frequency domain. So I'm saying, in order to test against arbitrary S0 function, take an approximation by something compactly supported. So K is compactly supported, and you look what happens with the dilation. And then you see, well, this is explicitly written. Actually, it should be rho S squared, not rho times S squared. But still, if rho goes to 1, this goes to constant 1. So I'm writing constant 1 as a function of S by a boldface of 1. Now, because the support is compact in between, here, when we have K fixed, we can write it for a fixed Q, and then this is going uniformly, and then it's clear that this will have in a limit just 1. This is something that you can do with Riemann integrals without problems. So we don't need something like Lebesgue-dominated convergence theorem or deep measure theoretic results, but we need the setting of a 0 prime in order to come up with such statement. A little bit less fancy, but something more close to what we have is do the same thing with the sinc function. Now, the sinc function is at least decaying, it's square integrable, but it's not integrable, so it's still hard to say what is the total mass of the sinc function and why is that going to delta 0. But the argument is now even easier. We know that the sinc function is the Fourier transform of the boxcar function, the rectangular function, symmetric, normalized in all possible ways. Because of the symmetry, sinc is an even function because the boxcar function is an even function. So the forward and the inverse Fourier transform are equal. So what I have to do is to find out what happens here. I go to the Fourier transform domain. So that gives me again the dilation operator, and by dilating a boxcar function, of course, I get a huge rectangular function. And that goes to 1 in a very naive way. If you are, again, testing as you did before, you would say, I'm testing against K of S. K of S is living in some ball of radius R. Now, once you are making rho so small, I see there is a problem here. D rho, it should be minus 1 over 2 rho up to 1 over rho. So either I write here rho to infinity, which is not good. I mean, it should, yeah. So there's something I have to correct. It should be the interval, which is bigger and bigger. And finally, for a compactly supported function, at for rho small enough, that interval rectangular function will be big enough so it's really equal. So the limit is constant 1. And you see it's now this is also one of the arguments why we should have this uniform boundedness. Now, before we go on and compare the different settings, let me describe the situation for how the discrete Fourier transform can be derived, or is in a way a special case of S0 prime. Now, when you see the discrete Fourier transform, you're normally viewing it as something that maps vectors into vectors. So in MATLAB, you have the FFT command. You have the FFT2 command, which maps pixel images, as I say, into pixel images. In a way, you can enter a matrix, you get a matrix of the same format. But for me, and I think this is a big advantage of viewing everything from the point of view of mild distributions is, but of course you can do it with tempered distributions if you're familiar with it, that's not the point. But you can embed it into the continuous world. So let me just quickly describe the situation from an abstract point of view and then go back to the concrete version. So if we are in RD, everything will be about sampling in a regular fashion. And we will use the expression, something is a lattice, if it's a subgroup with respect to vector addition. So you can have two lattice points, their corresponding vectors from 0 to the lattice point. If you add them up, you get another lattice point. If you take the negative, you have another lattice point. So you find out that the collection of points, this grid or lattice, as we say, is obtained by applying a non-singular matrix to the standard lattice. And of course, there is some kind of fundamental domain. If you take identity matrix, this would be just the standard grid. And you would say the fundamental domain is the cube minus 1/2 to the power d, or 0 to 1 to the power d. And the volume of the fundamental domain is 1. Now, if you apply such a matrix, for example, if you apply a dilation matrix, say in the plane you take a diagonal matrix with 2 and 3, you would say, yes, you're stretching the lattice, you're taking 2 in the x direction as a lattice constant, 3 in the y direction. And of course, the fundamental domain is stretched by the factor of size 6, which is the determinant. So the size of the fundamental domain of the lattice, which by moving along the lattice is covering the whole RD, is exactly the determinant of A. But that's not so important now. Now we will use as a standard lattice set D, because if we are talking about a coarse and defined lattice, then maybe the other lattice will be of the form B times set D. So we have A times set D and B times set D. But then you can apply A to the -1, and then you compare this lattice with another non-singular matrix to a sublattice of this. So we will work with, when we talk about coarse and fine lattices, we try to work with this here. Now, in order to be more precise, I would like to mention that if you transform, let's say, the plane, then you can also transform the functions accordingly. So something sitting at a certain lattice point, which has labels coming from the integer lattice, and you apply this transformation, you get a point in the standard lattice. But if you have a function concentrated at a certain marked point in the lattice, you would also transfer it back to this function. So this transformation, which is an affine transformation of the argument, also leaves the space as zero invariant. And the proof is more or less like the dilation proof. I just wanted to mention this here. Now, the important thing is that periodic and discrete measure is a sum of Dirac Combs. This is done in a moment. Sorry, I have to interrupt for a short moment. So I like to use this picture in the one-dimensional case, so it's kind of a description. If something is repeating in a periodic way, so we have now a finite example of what I'm doing in a general setting now, in abstract setting. So you would say the red values are repeating themselves at a certain frequency, and then the next one are the dark blue values, the yellow values, the deep small blue values, and so now I'm just saying that this periodic thing, and you can think of this being wrapped up, is repeating itself. So we take the red amplitude times the Dirac Comb, and of course the distance between red values or blue values or green values is always the same. So I'm rewriting, and that's the trick of showing what's going on. I'm rewriting my periodic sequence, and I'm writing the proof formally only for the integer lattice, but that's kind of the real situation, as a linear combination of finitely many Dirac combs, and they're at distance n. So that's how they are repeating themselves. So distance between equal values. And then it is good to start the labeling with 0. So it's like you're computing modulo 10, and then you would say the remainder could be 0, 1, 2, 3, up to 9. So we have a vector of length n, but in order to put the orientation correctly, we assume that we choose the labels to be from the value at 0 to the value at n minus 1. And that's also important to know. If somebody is giving you a vector of length n, why we say we would like to read it as a function on the unit roots of order n, and they are starting with omega to the power 0, and then we go clockwise or anti-clockwise through the unit roots. So that's kind of very natural. It's not natural when you do the programming in MATLAB, because you cannot call for a component number 0, otherwise so this is done kind of on paper or in your head or so. And of course, we're doing an integer shift because our fine lattice is the integer lattice. Now, we know what kind of rules we have for the extended Fourier transform. The Shah comb is a sum of Diracs. It's a linear functional, and that's simply because it's even a linear functional on the Wiener algebra, and S0 is inside the Wiener algebra. Or if you view it differently, well, what is a Dirac comb doing? Is summing up over all the point values of a function f from a 0 at the lattice point. Now, if you know what happens at the atoms, and the atoms have a finite length support, you know how many points you get, so you can control the effect of this Dirac comb when it acts on atoms, and by adding up, you can know it for every element in S0. So these are nice linear functionals on our space, so mild distributions. So they have a Fourier transform, and even if you shift these Dirac combs, you get this, and of course, shift by an integer gives you the character. Now, what is the Fourier transform of this here? Maybe I have put it at different places. This is a ST-row operator applied to the Dirac comb at the integers. So you're doing a mass-preserving dilation. You move everything from 1 to n, from 2 to 2n, from -7 to -7n, and so on. So it's just the ST-row operator. And we know, of course, that this means the Dirac comb goes to the Dirac comb, so the stretched operator goes to the dilated. And if I do it separately, this dilated operator gives you a Dirac comb which sits on the orthogonal lattice, or the dual lattice, which is just the set lattice with 1 over n and with an amplitude here. So whereas, yeah, okay, we will discuss this separately, but this is a formula that we can use. Now, multiplying a Dirac measure with a function means you have to evaluate that function, and the function is the pure frequency minus j, so it's e to the minus j of 2 pi I, and evaluate it at the points delta n, and so this is giving you what you have to do. So we have to take this. Now, this is not a good description. It should be written as just the chi minus j. So maybe I should write it as a function of t here. But when we have now the sequence a, so it should be a here, then you get a sum. The 1 over n is coming from the dilation operator, and that's now correct. If we see what happens here, so this term has to be corrected. But if we look at any given value, we see a Dirac comb, so maybe starting from here, a Dirac comb at lattice constants 1 over n. So this means we have all the deltas which are appearing at k over n. This Dirac comb is multiplied with the values. So here you see it's the frequency minus j. That's why you write e to the 2 pi I times minus j. Of course, I'm writing the minus in front. And then you're saying evaluate it at the point where the Dirac is living. That's why we have the k over n. And now you're looking at this Dirac comb, and you see that this is, again, a collection of shifted elements of a given Dirac comb. And now this Dirac comb needs n repetitions. Now the question is, what are the coefficients? And the coefficients are exactly the ones that you can get by this formula. So maybe I should add a little bit more text, but essentially we have applied the Fourier transform rules, invariance under shift goes to multiplication, dilated Shah distribution or Dirac comb goes to dilated comb with the opposite compression factor and the factor, and you get that this is exactly, maybe up to the constant, I think I have ignored this 1 over n. It is the discrete Fourier transform, this part is the discrete Fourier transform of the sequence. So the sequence BL is what you would call the discrete Fourier transform. Now, for the more general case of lattices, one is the coarse lattice of periodicity, and coarse lattice, well, I have beta here. The big lattice is beta, and the fine lattice is alpha. One finds so that you get something where the Fourier transform, in the distributional sense, is living on, again, a lattice. And the point is that maybe I have to show it in this way. The periodicity beta here of the original lattice gives you the sampling rate for the fine lattice. So it's 1 over beta. This is a smaller constant. Whereas the alpha is the sampling rate, and the sampling rate, the inverse gives you the periodicity, which is, of course, n times as big as the sampling rate now on the Fourier transform side. So this is something that is very important to understand. And I think for now, I think it's better to stop the course and resume after a couple of minutes. So I suggest that we take a break of 7 minutes or so, and you are free to ask questions.